welcome to the session. Greeting of the day. In the previous classes, we are on the talk of the solidification processes, and then in continuous with that, let me go ahead with the problems causing in the solidifications. What are the problems associated with the solidification process? That we see one by one. I am counting these three. These three are the important points to be considered for solidification. They are the shrinkage defects, hot tearing, and evaluation of gases. And you keep on remember those words. Shrink, you know these words already. Shrinkage defects, the molten metal got shrinking at a point. That is a defect. Hot tearing, the crack happens at a hot condition. That is one defect. And then the evaluation of gases, the entrapment of gas involvement in between the mold cavities. These are the various defects that we are going to see now. Right? One by one we will go. The shrinkage defects. What are the causes of shrinkage defects? Shrinkage, we know, it is contrasting. Shrinkage. What is the defect there? Insufficient size of riser. We know this. See, we have taken a box. From there, one side I want to feed, and one side the filled material have to come upward. Right? What is that? This here it is called as a riser. As we know, we have studied in the casting. But here, in case, what is the riser other name? We know this. We have already studied. This is also otherwise known as feeder. Also otherwise known as feeder. So, in case if the feeder is narrow, it is not sufficient enough to give the riser's duty, that is feeding system. The inbuilt solidification is not sufficiently, molten metal is not sufficient to reach the corner. It means where the specific need is there. It may solidify early. Therefore, insufficient size of riser is important factor for the shrinkage. What is the other point? Improper location of riser, casting designs, progressive solidification. We see one by one again here. So, what is the design of riser operating significantly larger so as to feed the casting cavity throughout the solidification process? It means the improper setup of the riser cause the non-feeding system to the object. So what happens here in the light zones, whether on the thin zones, the solidification starts in all the regions. The solidification starts at all the sides. It means solidification start here, solidification start from the top, from the left, from the right. All cases the solidification started. But in such cases of when the area is very less, heat dissipation will take very quickly. Therefore, it closes very fast. It closes very fast these regions. Therefore, what happens? This riser system cannot give the feeding operation to the large objects when it is solidified. Therefore, we are changing the design and fixing the riser at the right location. How we are changing? Instead of giving this riser in this location, I am giving in this location. What happens then? This is a heavy part. It means the large thickness area. Even though solidification, air involvement is here, air involvement is here, air involvement is here. It means the cooling process started quickly. So air involvement is here. What happens? As a thin part, in quickly, this air, this solidification, this cooling process takes quick. Therefore, what happens? It solidifies here. See, it solidifies here. But here also it is started. Here also it is started to solidify. Here also it is started to solidify. Then what happens there? Here also it is started to solidify. Here at the corners with respect to involvement in the air contrasts, it solidifies. But even though it takes more time to come to lock of the system, lock of the opening of the riser. Therefore, the feeding system is possible to the heavy object. In such cases, what happens? Here it is already closed. This region it is closed, but it is not closed. as because this thin region is kept opposite. Therefore, the cooling process, even though it takes place very quickly on the thin components, it is not disturbing the feeding system of the riser. Therefore, the design of riser system to be very paka. So therefore, place the riser in the right location. Place far away or not nearer to the thinner section. Why? The thinner section makes, we consider a small object here and we consider a large object here, right? So both are observed by both cases there is a air entrapment is there. So here also the circulation of air are observed by the specimen. So what happens in immediate with respect to these things, you see, the first layer will become cooled. This layer will become cooled. Here also this layer will become cooled by the air circulations. Okay. Now it is causes to cool about the second layer. What happens then? The second layer cools here. The second layer cools here. Then the third layer cools here. Fourth layer cools here. Likewise, it's completed. But the same cases, what happened there? As it is large, it takes more time to cool, right? So as discussed here, you see the second layer, first layer completed. The second layer it started to cool, right? In the meanwhile, it is 75% completed, and then the next layer, then the next layer, then the next layer. At last, we are getting the last layer filling. But here, what happened? Within the 3 layers, the thin section cooling completed. Okay, but here what happens? The thick section, it takes more time to cool. Therefore, what I am doing, this occurred by the progressive solidification. But this occurred by directional solidification process. Okay, so for the same example I am taking in this way. I have taken the specimen for this like this, and I have taken the specimen for this like this. So what happens here? We have considered entrapment in all the directions. Here also entrapment in all the directions, right? But what happens? Cooling process. Cooling takes place here. Slowly it closes. It is perpendicular to the axis. Means the radial direction. But here what happens here? Here also the solidification occurs here. Occurs here. But in the meanwhile, the directional solidification also occurs in this way. In this way also the directional solidification occurs. Therefore, directional solidification is good rather than this solidification process, perpendicular solidification process. Why? When I am adding a feeding system here, this feeder of molten liquid should pass away to the entire location up to this corner to fill. In case in progressive solidification, this is not possible. It is stopped here because due to perpendicular progressive solidification process, thin section, it is solidified quickly and blocks the region and not permitting to go here. It is not permitting. But there, even though at the corners progressive solidification is there, at the center directional solidification is there, starting from the other zone to this right to side to left zone, this feeding system works well because the thick section at the borders there is a progressive, at centers there is a direction, the feeder goes inside and it helps to reach the corner. So that is a point we should understand this. So you see the same diagram I have given here also. The same diagram I have given here. So direction solidification which happens in the axis direction, therefore this helps the riser system. Riser can go up to the last end, it can reach. But here it is not possible, even though the riser is here. When I am reaching here, the arrows will indicate perpendicular. It blocks and it cannot possible to move there. What is direction solidification? In the direction of flow. In the direction of flow, this is, when I am putting the arrow in this direction, this is a directional solidification. I am putting the arrow perpendicular, this is progressive solidification. But the same both happens. When the air interaction, progressive also happens. At the same time, this side directional solidification also happens. But how we should design? Design we should do for the ability of directional solidification only. If in case progressive solidification happens perpendicular, it will close here. If it closes here, what happens? I have designed the same concerns little bit thin here. This design is not here like this. In case the design is like this, what happens? In immediate, this air interaction will happen here. The air interaction will happen here, and then it closes. Then the feeding system will not work. Then it forms the cavity here, right? So we should broadly have, and we should try to make the direction solidification. It means the broad area should give. Where is the broad area? There we should provide the riser. That's the design criteria. Okay. Direction, the definition. Solidification progresses parallel to the axis of casting. Towards the riser. In such cases, riser can feed. And otherwise it may not be possible. So progressive solidification process is perpendicular. Solidification process where it is perpendicular to the axis of casting, slowly closing to the path riser to the feeding of the possible. So I am recommending the directional solidification to be happen. Second one, the improper design of casting. So we should give here the improper design happens here. How we can give? I have terminated this design. This part I have taken out. This part I have taken out. This part I have taken out. I have kept straight, and one more design I have did. Instead of this sharp corner, I have made the curved path here. In such a way, the molten metal will flow smoothly. Right? Therefore, we can do like this. So such design ideas we should do. How this, even though that as per design we need, but some smoothing, this idea making of riser changes, so such cases we can do. That is what. So I am coming to the factors influencing this progressive solidification. So we understand progressive solidification should not happen. So what are the points how we can able to stop those progressive solidification and activate this direction? Direction, we know it should go in this way. We know direction solidification is the axis and progressive solidification is the perpendicular. We know this now. Okay, perpendicular. So now what happens? There are few points are there to consider. So first point I am telling, high conductivity materials and high heat capacity results in steep gradient and high degree of progressive solidification. What it means? We have taken high conductive material and high heat capacity materials. What happens? We have taken a material which contains high conductivity. It absorbs more. It absorbs more heat. Then it will be. I am drawing here the two lines here. See, this is the line representing. This is the line represent. Y-axis represents the temperature, and x-axis represents the time. Right now, for high conducting material, we have a liquidus temperature at this point, and we have a solidus temperature at this point. there's a gap between, there's a minute gap between this solidus line and the liquidus line. We know what is liquid and what is solidus line. I have already told you for copper nickel conditions. So this is the liquid and this is the solid. This is the liquid plus solid. This is the transaction zone. We call it as mushy zone. Okay, this region for high conductive material is very less. How it will be? It will look like very less. So I am drawing here. See, it very thin zone. You see, this is a very small gap I have. So what happens? This is a small gap. So we have a small gap here, not large. So it forms very quickly. So liquid to solid, it generates very quick. So that is what the timing I have given. So the time is very less. You see, the timing is very less. So this is very less time. This gap, okay, I can draw like this. So this gap. But see there, the low conducting material. For the low conducting material, the low heat capacity results in mild gradient of low degree of temperatures. What? How? This having more, it means the transaction between the liquid and temperature takes more gap. This gap is there. So in between those time, it can able to go for directional solidifications. When it is quick, it is a conducting material, it is quick, it dissipates the heat immediate. But the same cases for the low conducting material, it conducts very slowly and it dissipates the heat very slowly. It means the corners, the surfaces at the borders won't be quickly solidified. Therefore, the directional solidification occurs in the low conducting material. So how there, you see, I am drawing the same diagram here. I am drawing the same diagram. Y-axis belongs to temperature, x-axis belongs to the time. How much time it takes from liquid to solid transaction? It takes this much time. It is very slowly increases. The graph shows the time. It slowly increases, but here it increases in a minute. In case it takes 5 minutes to reach from liquid to solidification, it takes more than 15 minutes of time. For example, I am telling. Therefore, low conducting material, this is important. This word is important here. The high conducting belongs to progressive. This low conducting not belong to progressive. So this is direction. We need low conducting material. Keep remember, we will go for comparison also there. So the second one. What are the other point? We told high conductivity, progressive. Low conductivity, non-progressive solidifications. We know progressive is perpendicular and the directional solidification is axis. We know these points. So now second point, short freezing range. The short freezing range results in high degree of progressive solidification. What is short freezing range? I am taken two materials. Of steel or aluminum and magnesium, which is having the aluminum having the melting point of 360 and magnesium having 660 and magnesium having the melting point of 650 or 640, like that. So both having the freezing range between these two is very less. One material melts at 660, one material melts at 640. When I am combining these two, the common alloy system having the melting range around 650. Right? So it changes from liquid to solid in a specific time. In a specific time, there is no less time is there. There is a less time of transaction between this time liquid to solid transaction, freezing. There you have what the word we are using is the freezing range. So here liquid to solid is the freezing. Change over time from liquid to solid, the freezing time. The range is very small. This is what they have given here. See, again we have taken axis at y-axis at temperature, and x-axis is time. We have a small range. See, this is the curve. Here is the liquid, and we are getting a small line here. In between this small setup, it changes to solid. Therefore, this is short range materials won't go for directional solidifications. Now, on the other end, long range results. See, this long range materials, long range freezing ranges results in low degree of progressive solidification. It means it's directional. How long it takes? See, how long it takes? Here it takes this ranges. So see, this ranges, this setup. I want to explain you this one. From the liquid to the solid, it takes more. This time, this is the time we should understand. Here it takes less time. Here it takes more time to convert from liquid to solid. Here the freezing is very small. We have taken the alloy system, aluminum and the steel. In case, aluminum and magnesium for these cases. In such cases, we have taken steel and aluminum. Likewise, we can consider one alloy system should contain long freezing ranges. If it is less freezing range, progressive will happen because there is no chance. The time taken itself very low. Liquid to solid transaction takes very immediate. But there, what's the case here? We have a long time. A long time happens. The curve may be like this. So even here it is liquid, here it is solid. It takes more time to change over. Therefore, this is represented by here, the time dependent. So short freezing range, progressive. Long freezing range, it is directional. So this also we understand now. Now next, the third point, what are the other chances? High freezing temperature. The words are similar, but little minute variations are there. The high freezing temperature results in steep gradient. Now let us consider, for example, we are heated to high temperatures of material. It is differ from the room temperature. When we are at 1500 degrees centigrade, when it is quickly kept at the environment, the gradient, the temperature gradient between 1500 and the room temperature is very high. What it makes? This makes a fast cooling process. Now, let us consider one more example. One object is at room temperature and one object is at 300 degrees centigrade. This temperature gradient is very small. This cools slowly when compared to the high temperature gradient material. Therefore, if the freezing point is high, obviously it starts the progressive. If the freezing point is less, obviously it starts for directional solidifications. Now see the example. Here we have high freezing temperature. The temperature is here. Here the temperature is here, and the material's freezing point is kept at a high temperature here. Liquid to solid, this is a very steep. That we see in the previous point also. This freezing range is also very steep. And also the temperature gradients also high. At range of 1500, the temperature gradient between the environment or atmospheric temperature, it is very high. Then it should come from high to low. It should come from high to low. Therefore, it acts as a progressive solidification. It finds an easy path to solidify. But here, the temperatures here, we have taken low freezing material. Likewise, we can take as aluminum here, and likewise we can take as a steel. Steel having 1500, when it is cooled, it should come from 1500 to room temperature. And similarly here from aluminum, as compared to here, it is 1500. It is 1500. But here it is around 660, around 650. This should come to 650. This should come to 650 to 35 degree room temperature. But here this should come to 150 to room temperature, which contains more temperature gradient. This steel contains more temperature gradient and high freezing point there. But here it has low freezing point and less temperature gradient, and also take more time. See, more time to cool down. So this is why this high freezing belongs to progressive. High freezing belongs to progressive, and low freezing belongs to the not progressive case of solidification process. Both happens, we understand clearly, both happens, but even though directional solidification should be there, then how we have to select? We have to select the low freezing point, we have to select the low freezing ranges, we have to select the low conductive materials. These are the 3 points which will be helpful to avoid the progressive solidification process. If the progressive solidification happens, what happens? It closes perpendicular to the object. It closes the path. If it is closes, the feeder system cannot go inside. Then if the feeding system is not good, shrinkage defect happen. We are on the talk of shrinkage defects. That should not happen. So we should avoid progressive. Right? That is what the point. Right. Now I want to conclude. It means we have seen already these 3 points. We have already seen these 3. Now we want to see what the comparison. What we have seen. I have written there. See, the progressive solidification and directional solidification I have compared. How I have compared? I have taken a high conductive and high heat capacity results in steep gradient and high degree of progressive solidifications. Right? This is what the progressive. See? Progressive solidifications. So high conducting material, it absorbs heat and releases heat quickly. Therefore, if it is quick, it finds the easiest path to react to the environment to give the heat from its object to the atmosphere. Then it is quickly, the temperature transaction takes place. Therefore, the progressive solidification initiated. That should be avoided. There what happens? Instead of high conducting material, we have a low conducting material here. This initiates the directional solidification process. Now, at other points, this is number 1. It should not happen. Number 2, this also should not happen. High freezing temperatures, like steel, like aluminium. High freezing, the graph we have seen, we remembered now. High freezing temperature should not happen. High freezing temperature results in steep gradient. It means the difference, the temperature gradient steep. It means 1500 to room temperature. That also we understand. And high degree of progressive solidification chances. This also progressive solidification initiated. This also should not happen. Here it is high freezing temperature, and this side it is long freezing temperatures. The liquid to solid transaction to take long time. This one, okay, it should take longer time. This longer time needed. Here it is very short. This results in progressive solidifications. So likewise, and the last one, short freezing range. That is what the temperature is 1535. This transaction is liquid to solid. In what time it is? In a short time or long time? That is a temperature timing range. Short freezing range results in high degree of freedom. This also results in progressive solidification. This also should be avoided. Then what I am doing here, long freezing range. Instead of short freezing, I am going for the long freezing range. This results in directional solidification process. Very, very important point, very simple point. High conductivity, low conductivity. High freezing, long freezing. Short freezing range, long freezing range. So it should not be short, it should not be thin. The temperature gradient should not be very nearer. No conductivity, high conductivity should not be used. These all points belong to progressive. Progressive, perpendicular should not happen. Again, I am comparing the other 2 parts here. What is this? We are continuously talking short freezing range alloys, long freezing range alloys. They will ask an important question. They will ask in 5 mark or 8 mark question. Let's see. I have taken 2 examples here. For short freezing, the name says short freezing. I have taken the aluminium which have the melting point at 660 and the magnesium which have the melting at 650. What is the difference here? The range. Short freezing alloys. This one alloy and this magnesium, we are combining both to make the alloy system. So this contains 660 and magnesium contains 650. The alloy is combined. What happens? The ranges may be around in this same, in the 650, 640, 630, 660, in this range. So this ranges should be expanded. How? I have taken on the other side. The difference between the word, you you should keep remember the difference between the alloy freezing temperature is very narrow. In case if it is narrow means very nearer, then it goes for short freezing range. If it is short freezing range, obviously go for progressive. Right? Difference between alloy freezing temperature is long, aluminum 660. Here tin is 232. If we are combining this system as alloy system, this with 2 we get in the middle range of 400 or maybe 350. Some ranges we will get changeovers. So this is a long freezing alloys. The name says this initiates the directional solidification. This initiates the directional solidifications. So we understand. Possibly for this case, a short freezing I am telling. Possibly two zones, liquid and solid. The liquid and the solid short freezing range. What is this point it mentions there? In case if it is short freezing, we want to find the gap between this liquid and the solid. We want to find for freezing, we want to find the formation of liquid to solid very narrow. It is liquid, it is solid. In between, what should come there? Liquid plus a solid zone should be there, but it won't be there because it is very short. Within a degrees it forms there 6 to 640. The alloy system combines in a very nearer zone, so that third zone's mushy zone will not be there. But there chance of 3 zones: liquid, mushy, so I have mentioned here, mushy zone and the solid zone. For these conditions, how it will be? For these conditions, long freezing. How it will be? For these cases, it will be like this. So here it is liquid, here it is mushy. It means liquid plus solid. Here it is solid. Okay? For short freezing range, it will be likewise, and the very thin will be there. Very thin will be there. Right? We understand these cases. Okay? So likewise, so likewise, very thin will be there. Okay? So this is one point. Next one, leads for centerline shrinkages. Sometimes if there is no possibility of formation of solid to liquid to solid, the mushy zone is not there, then it forms centerline shrinkages. These are the other chances of formation. These are the chances of other formations are there. Now let it be. The fine dispersal shrinkage porosity may occur here. As it is, liquid zones are there. Some of the liquid may convert, some of the liquid may not convert as a solid finally. So there will be fine dispersal shrinkage porosity. Some small porosity or chances are there. Here, there is a chance of porosity. Here is a chance of shrinkage cracks. Next point: directional solidification does not help. Our solidification front is progressive. This word I termed, this belongs to, this directional belongs to there. See, this directional word belongs to the long freezing alloys. Okay, here I have written directional solidification does. Directional solidification does. But here directional solidification does not does. See, directional solidification does not does. Here it is does. Long range directional, short range progressive. Right? This is how we have understand this formation of shrinkage defects. Another two are there. We are talking about hot tearings and the evolution of gases. Next one, hot tearing we go. See, this is how it is. The differential contraction of chemical composition may happen. chemical composition may happen. Therefore, the chemical composition reacts, maybe sulfur and phosphorus we are adding there for the easiest path finding. Maybe maintenance of the molten metal. The property of sulfur maintains liquid or maintains the molten metal in such a way it reaches all the cavities, all the position of the box. But here, the same sulfur or phosphorus, if it is chemical composition is high, the percentage of sulfur and phosphorus is high, it leads to some other chemical reactions and forms the shrinkage and forms the crack. Therefore, it is not possible. Therefore, the chemical reaction should not be happened. Contraction may happen, and this long freezing ranges. Long freezing ranges are therefore causes the hard tearing. Hard tearings are possible there. The causes of hard tearings, importantly, these chemical reactions, chemical process should not happen. That will be causes the damages. Some reactions happens, it causes the cracks. So I have written here the 0.06% sulfur sometimes is useful. Sometimes it is useful for maintaining the molten metals, but improves the missionability, but causes the cracking at high percentages. So this sulfur percentage should not be increased. If it is increased, what happens? Results in hard tearing. This is one point we should remember. So we have talked about shrinkage defects. We talked about hard tearing. Then the evolution of gases is there. So the last one, the evolution of gases. What are the causes there? Evolution of gases. There is a chance when the casting box containing the wettability. There is a chance when the furnace having the wettability. These are the chances where the gases, water converted into gas, that we know. Atmospheric humidity. The environment where we are working, if it is wet condition, the same process when we are working it summer is different from the same process when we are putting the winter condition. Simply when the heater is operated at summer, it quickly heated. The same water when it is heated at the winter condition, it takes more time. Therefore, when the casting of box is utilized for the longer time, there is a wetness in the box in the winter season as compared to the summer. It won't be. In the same condition, when we are going for the second cycle, the wetness will be there. That is what atmospheric humidity. The wet metallic charges, the fuel, the coke, that may be wet due to the winter sessions also. Wet furnace, see, wet furnace, wet metal, wet humidity, this all belongs to environmental water conditions. Wet foundry instrument, with the instrument what we are using, we understand here, the metals, the furnaces, the environment, the instrument, what we are using, all belongs to this, the wet fluxes, the fuel coke that we are using, wet fluxes. Furnace fluids containing the hydrogen, this all makes possibility of creating the evolution of gases. So these conditions are not possible to make chances of creating of the porosity inside the material. Porosity inside the material. This evolution of gases will happen. Then what happens if the box is closed? So these are the defects. The casting is solidified, but it is less than defective process. Right? Therefore, we should be very ready to overcome this defective processes. Right? So the summary of this session, we have talked about in this class about the solidifications, and in the solidification we have talked about the progressive and the directional, right? And also later we have talked about the solidification defects. Such as evolution of gases, hot tearing, etc. Right? So these are the classes of today. The remaining part of the subject will continue in the next session. Thank you.